Hello everyone, I'm Nitin Reddy from ECB section. Today I like to describe about Rayleigh genes describe the radiation from a black body. Introduction. The black body notification is an important in studying thermal radiation and electromagnetic radiation energy transfer in all wavelength band. Black body as an ideal radiation absorber and it is used as a standard for comparison with the radiation of real physical bodies. Characteristics are sometimes are used to describing and studying artificial electromagnetic radiation in radio and TV broadcasting and communication. Concept of black body. Why black body we need? Because those bodies that absorb instant visual light will seem black to human eye. Example, we can hardly characterize our sun, which is indeed almost a black body with a very wide band of electromagnetic radiation, wavelength as black physical absorption energies. Is namely bright white sunlight which represents the equilibrium place black body radiation. Application. Optical band. Surface approaches an ideal black body in their ability to absorb radiation, such as soot, silicon carbide, platinum, and golden medium. Its surfaces. Water surfaces, ice, land absorb infrared radiation well and in thermal higher band. These physical objects are ideal black bodies. Here are some diagrams of black body. Definition of black body. A black body is an ideal body which allows the whole of the incident radiation to pass into itself without reflecting the energy and absorbs within itself this whole incident radiation without passing an energy. This property is valid for radiation corresponding to all wavelengths and to all angles of incidence. Therefore, the black body is an ideal absorber of incident radiation. Black body radiation laws. First, the Rayleigh-Jeans law. It agrees the experimental measurements for long wavelengths. It predicts an energy output that diverges towards infinitely as wavelengths grow smaller. The failure has become known as the ultraviolet catastrophe, where the formula is I equal to lambda t equal to 2 pi c kt by lambda 2, lambda to the power of 2. Ultraviolet catastrophe. You've seen the graph of ultraviolet catastrophe. The formula I of lambda equal to 2 pi c kg by lambda to the power of 4. This formula also had a problem. The problem was the lambda term in the denominator. For large wavelength, it fitted the experiment data, but it had major problem and it shorted wavelengths. Blackboard radiation law 2. Second is Planck's law. We have two forms as a function I pi gamma t equal to 2c square by lambda to the power of 5 by hc by e lambda t. As a function of frequency, the Planck's law gives a distribution that peaks at a certain wavelength, but peaks shift to shorter wavelength for higher temperature, and the area under the grow rapidly with increasing temperature. With the two graphs here. Comparison between classical and quantum mechanics. There is a good fit at long wavelength, but at short wavelength there is a major disagreement. Telling units. When Thailand is equal to infinity, but black body equal to 0. Third law, Wayne's displacement law. It tells us we eat an object of color changes from red to orange to white to R. We can use this to calculate the temperature of stars. The surface temperature of the sun is 5778 K. This temperature corresponds to a peak emission equal to 502 nanometer equal to about 5000 amps. V is a constant of proportionality called Wien's displacement constant and equals to 2.897 into 10 to the power of minus 3 meters, where K equal to 2.81 into 10 to the power of 6 nanometer. Fourth law, Stephens-Boltzmann's law, gives the total energy being emitted at all wavelengths by the black body, which is the area under the Planck's law curve. Explain the growth in the height of the curve as the temperature increases. Notice that the growth is very abrupt. sigma 5.67 into 10 to the power of minus 8, known as the Stevens-Boltzmann constant. With the graph we have given, computation of Rayleigh's lengths with Wien's law and Planck's law for a body of 9. Applications for black body. The area of its disk as viewed from space is area equal to pi r square. The total energy incident on Earth is incident energy equal to pi r square to S naught. The energy absorbed by the Earth's atmosphere system as viewed from space is absorbed energy equal to pi r square S naught minus A. As we know, the bodies must be in radioactive equilibrium. The solar energy striking its disk viewed from space is emitted and thermal radiation by the surface of the entire globe, as described by the Stephen Boltzmann law. Estimated energy equal to pi r square and equal to E square. As the absorbed energy equal to the emitted energy, pi r square S naught 1 minus A into equal to pi r 4 pi square is equal to T to the power of 4. Solve for T yields here the conclusion. As the temperature increases, the peak wavelength emitted by the black body decreases. As temperature increases, the total energy emitted increases because the total area under the curve increases. The curve gets infinitely close to the x-axis. Never touch it. The black body is a theoretical object that absorbs 100% of the radiation that it's. Therefore, it reflects no radiation and appears perfectly black. Roughly, we can say that the stars radiate like black body radiators. This is important because it means that we can use the theory for black body radiators to infer things about stars. At a particular temperature, the black body could emit the maximum amount of energy possible for that temperature. Black body radiation does not depend on the type of object emitting it. Entire spectrum of black body depends on the only one parameter, the temperature. Thank you.